of you as my witness. I am starting the stream. I am not going to forget again. And I'm going to share my screen so that you guys can see what I'm looking at. How's that sound? All right. So we started talking about path models last time. What do you remember about path models, like these things? Pictures. There's pictures, yeah. So what does it mean in the picture if you see a square? Yes, they're real. And if you see a circle, yeah, latent or pretend or errors. But they're things that have to get sort of found that don't already exist. Arrows matter in terms of directions. So what the arrow is pointing to is an outcome. Where it comes from is the predictor. So for instance, in slide 5 here, x1 is pointing to y1. That means that x1 is the predictor and y1 is the outcome. If you see an arrow that has two sides to it, that is a directionless association. That is just a covariance between the variables. And so they're allowed to be related without saying which is causing which. Are we doing causal modeling? No, we are not. We have a covariance matrix and we're trying to create a model that adequately captures it. We can't make any sort of causal claims without the proper design to back them up, and most of the time that is not the case. So even though causal modeling is a synonym, that is not what we're doing. What we are doing is multivariate models in which a given variable can be both a predictor and an outcome simultaneously. So for instance, I'm on slide 8 here. If I have y1 in the middle of this picture, it is both an outcome of x1 and it is also a predictor of y2. So these are the sorts of models that type of association that path models are very well equipped to be able to capture. We talked about what happens with missing data, and that was hella confusing, right? Maybe. Yeah, so the long and short of it, what happens with missing data depends on your software, your estimation method, and whether the missing data are for the predictor versus the outcome. If you are doing limited information, where what the model is working with is a summary of the original data. So to fit these models, technically all you need at a minimum is a mean, a variance, and a covariance. Like you just need to know what those are for all the variables in your model, and you can actually just use that to estimate path models. If you were to do that, none of the variables can have missing data or they're dropped, just across the board. If you use full information maximum likelihood, which is what we've been doing this entire class, that is when all of the original data are going into the analysis. Then you can have missing outcomes. If you have a predictor in M+, it cannot have missing data. But you can make M plus make it an outcome, so then it can have missing data. And that is what Stata does for you without your permission. In Stata, even like x1 and x2 in this picture, inarguably are predictors, right? They are not outcomes of anything else. But from the perspective of the likelihood function, they are in it. They are outcomes, which means they have distributional assumptions, which means you can have missing data on them. So we'll get a chance to see hopefully some examples today where you'll see this distinction play out. But then what you count in terms of which covariances are being modeled depends on whether or not it's in the likelihood or not. So if all 4 of these variables are being treated as outcomes, then all of the associations between them are things that the model has to capture. Those covariances matter. If x and 1 are just predictors, like in M+, they're not in the likelihood function, then the model does not have to account for their covariance between them. So it gets to be very confusing what is and what isn't, what has to happen. We'll see examples of that, and hopefully that will get a little bit better. Okay, tell me about identification. There's a new vocabulary word. Do you remember anything about that? Jeff does. Jeff had a lovely mnemonic. Would you like to share with the group, Jeff? Yes. Yes. Over-identified. That is a situation in which there are more covariances in the data than what your model predicts directly. So over-identified means you have overlooked, as you said, I'm going to steal that, some of the possible pathways. So you've estimated fewer parameters than you possibly could. The idea of degrees of freedom in these models has nothing to do with people. It has everything to do with the number of variables that you have. So in terms of information going in versus parameters coming out, all variables in the likelihood have a mean that gets reproduced perfectly if each variable gets its own intercept. So check. We haven't sacrificed anything there. The means and intercepts will align perfectly. Likewise, every variable in the likelihood has a variance to start out with. So long as each variable gets its own residual variance as part of the model, then the total variance will be perfectly predicted. So you've spent all your degrees of freedom there. Everything is perfect. Where misfit comes in and where identification matters is in the total number of covariances that are in the data and the total number of parameters that you are using to predict those covariances. So there's only two choices. You can either have a directed arrow in which you're saying one variable predicts another, or you can have an undirected arrow in which you are saying they just covary. Either one puts a relationship between the two of them. They fit the same. So if you have fewer of those paths than what you could have, you've left some out. That's what's known as over-identified, and that's where you need to worry that the ones that you've left out should really not be there, like that you haven't missed anything. And that process of making sure that what your model says the patterns of relationship is and what the data say they are match, that's the process of testing model fit. You guys have seen this already in a limited case. Do you remember talking about the types of R matrices that you can have in multivariate models? Maybe? Like unstructured? That one? Everything gets to be what it wants? And if you constrain the covariances to all be caused by the same correlation, that's compound symmetry heterogeneous. And if you constrain all the variances to be the same, then that's compound symmetry. So that's one example of this. Like you're trying to see if you can get away with capturing the pattern with fewer possible parameters by putting constraints, forcing things to be the same. When you omit direct paths, you're saying that there is no relationship between a pair of variables that isn't already captured by the model. And so we have to be able to believe that that is the case before you can interpret the results. Otherwise, all the numbers could be off because they're trying to account for a missing relationship that's not in your model. So that was what we were talking about, I think, at the end of last time. Fit in all of that. So this is slide 17. How about we pick up there? So degrees of freedom in this case, this is an over-identified model on the top because x1 to y2 is not there. So what this model says the relationship between x1 and y2 should be is this path between x1 and y1 multiplied by the path between y1 and y2. So the model is saying that x1 and y2 are related, but they're only related because of their shared connection with x1, or y1, excuse me. So the two paths multiplied together get to the relationship between those. That could be wrong. So you have 1 degree of freedom, 1 missing path to worry about. If you put the path in, there's no degrees of freedom left. You've put in as many direct connections as there possibly are in the data, and you can't be wrong. So for path models, this is generally a good strategy. Put everything in. Then you can see, based on whether a given path is significant, whether or not you need it. You can't do shit like this at the bottom, okay? The technical term for shit like this at the bottom is underidentified. So you can't have two paths to try and recreate one covariance, for instance. And you'll see people do crazy stuff sometimes in path models because they're thinking in terms of the pictures. But generally speaking, any one association can only have one path that describes it. There's no way to piece those apart. Okay, so we looked at that picture. Can you guys still hear me okay? Yeah, we're good? Okay. All right. We looked at tracing rules. So generally speaking, you can get what the predicted association is between any two variables in a path model by following the paths along them. So if I wanted to go from A to F, for instance, then it would be whatever the value is for the slope that relates D and A times the slope between D and E times the slope between E and F. That gets me all the way through. So even though there's not a direct path between A and F, the model says there is an association. Likewise, you can get from C to F by going along this path in here, but you can also get there by going over to B, then to D, then to E. So another way of thinking about this is just like in regression, when you put multiple predictors into the same model, their effects become the unique effects, right? It's the effect of, for instance, in this picture here, we have variable E that's being predicted by both D and C. So the effect of D is the unique effect of D after controlling for C. The effect of C is the unique effect after controlling for D. So the idea that unique is only part of the full association, that's why we have to take into account all of the other ways to get there. So the total relationship between C and E is not just the part that's unique. You also have to take into account the common part associated through correlations with other variables. So there's also a relationship between C and E if I go over to B through the curved arrow, down to D, and then over to E. That's the total relationship between the two variables. Back together again. And the total relationship in terms of covariance, which, damn it, I forgot to fix that. Sorry about that. Has a predictor variable's variance in it as well in those cases. So then we look through all of this, and this slide alone, can I just get a shout out for this slide? This slide took like 2 hours just to get all the tiny little subscripts and things correct. I hope it's correct, but like, look, math, see? I'm rigorous. I can do math. I can make PowerPoint slides that say math, but so you can through these rules, you can work out what the model says the association between any pair of variables should be. In practice, you get the software to tell you that for you. Yes, I did work really hard on that. Thank you. Yeah, it's these little things take so long to like do the little but anywho. So we were talking about absolute fit, right? I think that's about where we left off, right? Does that sound right? Yeah, maybe. Are you guys there? Hello? Everyone looks a little sleepy today. So I've already had my allotment of caffeine. I have placebo due, and I decided I needed a straw because the can kept hitting my microphone. So, plus my dentist a long time ago told me that I should always drink soda with a straw so that the acid didn't like wash on my teeth. And given that I'm never going to go to a dentist again, apparently, or to anywhere else for that matter, I probably should listen. So we're doing the straw now. So yeah, we're talking about model fit. How do you know if it's okay that you left out some of the paths? That's what you want to know, okay? Because if it's not okay, then you can't interpret any of the numbers because they're all going to rearrange themselves to accommodate missing things that should be there, and they won't be right as a result. So in trying to assess model fit, whether or not the model predicted patterns match those in the real data, that's what model fit means. It is going to estimate two other baseline models for you. So saturated model is just all the covariances. Like we're just going to recreate what the data say. Independence model or null model says there aren't any covariances. So it's like best case is saturated, worst case is independence. And the log likelihood values from those two models get used in creating additional what are known as absolute fit statistics. So we have a whole new set of acronyms that you get to learn in assessing fit. So there's 4 steps in assessing model fit. Global fit, local fit, making sure all the parameters make sense, and then considering effect sizes. So in doing all of the models that we've done up to this point, we haven't ever talked about 1 or 2. Like that's a new idea that happens in multivariate data, making sure that you have adequately modeled the covariance. So the primary index of model fit is a likelihood ratio test between the model you fit, which is known as the HO, and the saturated model, which is the H1. And you will never ever forget that you are the HO, right? You are the HO. That is your model. The H1 is the perfect one. So this is an instance in which a likelihood ratio test, minus 2 times the difference in log likelihood, tells you whether or not your model is worse than the saturated model. What you want is a non-significant result. This is one of the few times in statistics that that's the case, because what you're testing is whether a simplification is acceptable. So if I have the H1 saturated model that just has all possible paths or covariances directly in there versus what I have where I may have left some out so that it's over-identified, then if my model is significantly different than the saturated model, that's bad news. That means that the things I left out are causing problems. So ideally what you want is for your likelihood ratio test, it's known as a chi-square test, it's always what it's labeled, to be non-significant, which means that what you've left out could stay out. It's sufficiently zero to where you haven't messed up the patterns. In path models, that is usually okay unless you have a whole lot of people, because the chi-square statistic, the likelihood ratio test, is very sensitive to sample size. So in practice, people don't just report that. They report a whole slew of other indices that are rooted in either the saturated model fit as a baseline or the null model fit as a baseline. So I will show you all of these. So we're talking about other indices of model fit. There's one called the SRMR, which stands for Standardized Root Mean Square Residual. If you were to convert your data into a correlation matrix and then come up with the correlation matrix that's predicted by your model, this gives you how far off on average each of those correlations is. It's in squared terms. That way the positives and negatives don't cancel out. You want this number to be less than 0.08 or so. There's also the root mean square residual that is based on not the correlation matrix, the covariance matrix. That one is reported less frequently. So in general, with these indices of fit, if they have the word residual or error in the name, then you want them to be as small as possible. If they have the word fit in the name, you want them to be big. So direction matters here. So this is one of the ones you want to be small. So it's how far off on average the square correlation is. Here's a big one. This is one that is very commonly reported. Root mean square error of approximation, or RMSEA, people say. This is a statistic that adjusts for parsimony. So it's like how far off per degree of freedom remaining. So if you add extra crap to your model that doesn't need to be there, RMSEA won't like it. It can actually make your model fit worse because you're adding unnecessary parameters. So it's kind of like BIC in that sort of idea. It ranges from 0 to 1 and smaller is better. And people have had a really fun time coming up with verbal labels for what these values mean. This is just a smattering of these. Less than 0.05 is good. And then much like you can have something be approaching significance at 0.06 or marginally significant at p equals 0.07, we can have like, it's not good, but it's acceptable or it's not great, but it's not terrible. Like, and then you get into anything above point 0.1. I tend not to use words in my results section because I don't want reviewer 3 to be like, you can't say that it's good, it should be called acceptable. I don't ever want to have that conversation, so I just say the RMSEA was 0.06. Like, say whatever you want. Just give them the value. The reason that this one is used so frequently is that because in addition to the point estimate for it, you get a confidence interval. And the confidence interval gives you a range of what it could be basically across replications, just like any confidence interval. And that really shows you how precise of an estimate it is. So if I have an RMSEA that's 0.06 and my confidence interval is, 0.04 to 0.08, that's one thing, right? Like I'm like, okay, that interval is all within sort of good territory. But if it's 0.06 and it could be anywhere from 0 to 0.12, that's different. That's like, okay, I really don't have a lot of information here to judge fit with. Um, so that happens when you have very small samples. You get these really wide intervals and a lot of imprecision. You also, in your output, tend to get a test of what's called close fit as to whether or not the RMSEA is less than 0.05. So absolute fit would be 0, close fit would be 0.05, and there's some logic by which people think that that's more reasonable. Whatever. We'll talk more about that in structural equation modeling. It doesn't have as much to do with path models, which tend to have very few degrees of freedom. So those are the ones that where smaller is better. The ones where bigger is better. The CFI or the TLI. These are relative to the null model instead. So you want them to be as different as possible. So CFI goes up to 1. Values above 0.95-ish are supposed to be good. TLI is also known as the non-normed fit index, and it goes over 1. So it can be, I don't know what the highest it can be is theoretically, but I've seen it over 1 in really good models, but 0.95 is the cutoff for that one as well. So these are the things that you would report in addition to the chi-square tested model fit. And how this works in practice is that people say, well, my chi-square was significant, but all these other things look good, so I'm just going to say it's fine. So you will see people say things like that. All right. How are we doing? Okay, so a bunch of numbers that tell you whether or not it's okay that you left out some paths. That's what we got here. So global fit is one thing, but that's not the end of the story. So I think most of you don't have children yet, but if you can imagine yourself someday as a parent, and let's say that your child comes home with a report card where they have a 3.0 average. And you being the perfectionist parent that everyone thinks you should be, you want to bring that up. Well, in order to be able to help your child improve their grades, you have to know what goes into that 3.0, don't you? Because they could have gotten 4 Bs, in which case they need to do a little bit more in everything, or it could have been like 3 As and 1 F. And then I'd have to know, okay, well, was in the F like in art, or was it in something that matters, like math or science? Then you have to know, like that would be a very different strategy for remediation. So you can think of global model fit as like your grade point average. It's an aerial view of the match between your model and your data. But to troubleshoot it, like if you get statistics back that say your model's not good enough, to try and figure out where the problem is, that's the diagnosis of local misfit. Like, why is the model not good? Where is the problem? And so to do that, what we have to look at is the literal mismatch between what the model says your predicted associations are and what the data say. And fortunately, software makes this very easy for you to do. There's residual options available in all of the programs that spit out the match. They give you the data covariance matrix and the model predicted ones and the discrepancy between the two. So it will highlight then any covariances that are not predicted adequately that are the cause of the model misfit. And so then you can decide to put them in. So these residuals, if you have a very large positive value, that means that your outcomes are more related than what you predicted. So you need to add a path in that connects them. They have some kind of unique relationship that's not being addressed. A negative residual is a lot harder to troubleshoot. That means they're less related than what you predicted. Um, so that one comes up much more in structural equation models that involve latent variables, not so much path models. But the positive residuals just mean you need a path there. There's various metrics by which these things come out. There's normalized, which works like z-scores. That's the one that is usually the most helpful at identifying what's relatively bad. But you can just look at the raw covariance matrix discrepancies as well. So let's see here.